any background noise from my side?
No, ma'am.
Hello everyone, welcome to week 9 of problem solving session. Sensitive space problem solving session. And this week we are looking at problems related to searching and solving. So I wanted to ask if there was time to help you look at the content of week 9 and understood what is searching solving from the place of solving related to searching solving. Can we go on? Hello? Yeah. So have you looked at the week 9 content and have you found that have you studied searching sorting environment? Have you or have you not? Can anyone answer? Okay, we're going to put that also. Okay, so problem 1 is, what is the best case complexity of ordered linear search and worst case complexity of selection sort respectively? And the 4 options, and we have to tell which is the correct one. Any answers? If you don't know what section is sorting this one, you can tell me, but I'm expecting an answer. Anything. Okay, so the right answer here is that the linear curve, the best case complexity is when the first element itself is the element that you are trying to search for. Then the first element will match your search element, and in that case, the complexity of the algorithm will terminate and the complexity is order 1. And the worst case complexity of selection sort is order 2 squared. So I will again ask, do you know about linear search and selection sort or not?
Yes, ma'am. You know.
Okay, so can you tell me what is the answer here
Option A.
and why is that?
Here, because the best case complexity of linear search is O1, O1. That is order 1.
Okay,
Yes.
and selection sort?
O1 square.
Okay. So let's move on to the next question. Which of the following is or are correct? First is binary search is applied when elements are sorted. Second is primary search is applied when elements are sorted. Second is linear search can be applied when elements are in random order. And third is binary search can be categorized into divide and conquer group. So which of the following options?
I think option B is correct. Yes, statement 1 are correct, statement 2 are false. And about the statement 3, I am not confirmed.
Okay. Okay, option 1 is correct. Why do you think that option 2 is incorrect? Okay, then you have to tell me how does linear search work? What is a linear search?
A linear search means when we search an element in an array by a simple linear method by a single line, by simple inner direction.
Okay, give me an example. And write the problem on the whiteboard. And then you can tell me. How will you search using linear search? So the question is first the elements are 12, 11, 13, 4, 5, and you are, this is your array, and you will see that you want to search for 5. And now we will search using linear search. Can you search using linear search or not? Okay. So linear search is an exercise. 12, 11, 14, 5. And the question, what we are interested in is that, okay, the question is whether there is an element in this array with value equal to 5. So how do you find that? Like, what is the most naive approach that we can use? So we will go to the first element and we will check is this element equal to 5 or not. Okay? So is this element equal to 5 or not? The answer is no. Then we move to the next element. Is this element equal to 5 or not? No. When you go here, the answer is still no. You go there. Yeah, this element is equal to 5, so I will return this position 6. Okay, I found the element at position 4, given that the index starts from 1. This is linear search of 5. What happens if 5 is not there? So 15 was here. Then we will compare it and your answer will be no. This is not 5. Then you go to the last element, which is still not 5. And you come out of the array, so you will say, okay, 5 is not there in the array. Is the algorithm clear? Is it clear? Really? This is linear search. Do you understand?
Yes.
Do you want me to repeat?
No.
Okay. So this is linear search. And here, as you can see, there is no ordering of the elements. The elements are randomly ordered, right? There is no ordering like the elements are from larger to smaller or smaller to larger. There is no ordering here. So here, since we are going and comparing with each and every element one by one, You can do it from left to right, right to left, whatever order you want to follow, but there is no ordering of the elements that is required. So that's why option number 2, linear search can be applied when elements are in random order. It's true. Now coming to binary search. How does binary search work? Let's say you wanted to find here again the element number 5. Then how will binary search work? Can we apply binary search on this array?
And research this array. Yes. Search it. If it is in ascending order, then we can apply the binary search.
Okay. Yeah, you're right. So, yeah, I can check the chat box. If there's a network issue, you can write it. And yeah, you're right. So here we cannot apply binary search necessarily because it is not sorted. So to apply binary search, we have to first sort it. And let's sort it in the ascending order here. So first we have 6, then 11, 12, 13. So this is our sorted list. And we can apply binary search in this sorted order. Now, what are we looking for here? We are looking for element 5. So how will we find element 5? What do we do in binary? We go and look at the middle element. Okay? Here middle element is 12. We go and look at the element which is in the middle of the array. And here 12 is the element which is in the middle of the array. So we are going to compare it with 5. Is 12 equal to 5 or not? So the answer is no. Right? Now what do we do? So we know that we're looking for 5 and we know that the array is sorted. So all the elements which are in the right hand side of 12, these elements, they are greater than 12. Right? Now, if the element which we are looking for is greater than 12, then we should look only in the right hand side. We should look only in this range. But we are looking for 5, and 5 is smaller than 12. So we should look in the left hand side. Because we will never be able to find 5 in the right hand side of 12 because all the elements in the right hand side of 12 are greater than 12. So 5 cannot be there. So that's why we discard the right hand side of the array here. We say, okay, there is no need to search in the right hand side because these elements are definitely greater than 12 and hence definitely greater than 5. So let us look on in the left hand side of the array. Now coming to the left hand side of the array, now we have reduced our problem. Earlier we were looking in the entire array. The entire array was our search space. Okay? Now we have reduced the search space to only the left side array. Now this is our search space. Now in this search space, we will again go and look at the middle element. Okay? Here there are only 2 elements. And let's say this is the index 0, this is index 1. So let's say this is the middle element. I mean that we can do by saying, okay, the first element is at 0, second element is at 1, and then we will divide by 4 and take the floor of that. So it comes out to be 0. So we are here saying that okay, our middle element is at index 0. So now we compare the middle element with 5 again. We check, is the middle element equal to 5 or not? So no, it is not 5. So if the middle element is not 5, what is the middle element? Is it greater than 5 or is it smaller than 5? So the middle element is 6, it's greater than 5. Okay? That means all of the elements which are in the right hand side are also greater than 5. These all elements which are in the right hand side, here there is only one element which is 11, that is also greater than 5. So we do not need to compare it with elements on the right hand side. Now we can look for elements in the left hand side, but there are no elements in the left hand side, and hence our search will stop here. Now we can say, okay, there are no elements further that I need to look at, so this array doesn't contain 5. So this is an example where we did not find the key we are looking for, but this is how the algorithm works. Okay, so first of all, if I will now just explain it in a very, without any numbers, like how it does it work. Again, you have a very big array. Okay, this is your array. Again, this is your very big array. Okay, and you are looking for some element. We will first go and look at the middle of this element. So this is the middle. Look at the middle, you check whether this is the element you are looking for or not. So if you're, then you will check if it matches. If you are looking for K and if this element is also K, then you can declare okay. You can declare that okay, I found K. But if it doesn't match, then you need to check whether the middle element is greater than K or less than K. If the element is greater than K, that means you need to look in the left hand side. And you can discard the right hand side. Okay. So then we will look for middle element somewhere, like this is the middle. So you go here, you check is this K or not. Now it may match. If it matches, then fine, you can stop your search. If it doesn't, and if it says that okay, the middle element is smaller than K. If it is smaller than K, that means all of these elements are also smaller than K, right? So you need to look in your right hand side, that means here. So if you will observe, every time your search space is reducing. Earlier your entire array was your search space, then it was reduced to half of the left side. Then in the left side also you again look for the middle, and based on that you choose whether you want to look in the left hand side or right hand side. That is, again you divided the array in half. So every time you divide your search space in two halves. First you divided here, saying okay, whether it is in left half or right. Then you went to the left half and you said okay, now whether it is in the left or right. Then you went to the right and again you divide. So every time you divide your search space by half, and that's the algorithm, and the decision you are able to take whether it is left half or right half is because the array is sorted. So based on that, you can say whether you will be able to find the first element in the left side or right hand side. So that is why the binary search algorithm is of course it is applied only on elements when they are sorted, and it is categorized as a divide and conquer algorithm because it divides the problem into smaller problems and then it solves that. Any question? Okay. So that's why the answer to this problem is 1, 2, and 3. So all of them are correct. Binary search is applied on sorted elements. Linear search can be applied on elements in random order. Binary search is categorized into divide and conquer algorithm. So now, moving on. What is the recurrence relation for linear search recursive algorithm?
No, ma'am.
Okay.
Ma'am, you're correct, friend.
Okay. Okay, so what's the linear search? If we just look very in the first column, linear search means that we have this array of elements, okay? We have an array of elements, and we're looking for I'll use the example again. Let's say you're looking for an element with value 5. So you are going to go at each element and check whether this element is 5 or not. So 12 is not 5, so you move to the next element, 11. Is it 5? No. Then 13, is it 5? No. And then you go to next element and you check, is it 5? Yes. So your algorithm will perform element 5 at the next step. Now, the question is saying, if you write a recursive algorithm, like you can write an iterative algorithm, which is just a for loop. So for loop, you will just go over each and every element and you will have written many for loops to iterate over this array, right? I is less than size of array and I said, yeah. So you just check if array I is equal to k, which k is 5, which you will control, then you will, if this is what you're looking for, then you can say, okay, you can print here, okay, from k as anything. This will be a iterative algorithm, okay? Iteratively, you can be like this. But now we have to write a recursive algorithm. Then how will you do that? So recursive means you will have to write a function, okay? And which can call itself again and again with smaller problems, right? So here we will have the recursive search. And we are passing with an array in which we want to result. And we're passing, let's say, unfortunately my browser got clear. But it looks clean as a pretty right?
No, ma'am.
Right? Can you see the screen? Okay. will move forward. I hope you can see the screen. On the left hand side, I've written a follow to search for a given element which you can case. And on the right hand side, now I'm writing the recursive reverse search. So recursively, we are going to look in the array to find for an element K. So ARR is our array in which we want searching for the element, and K is the element that we are looking for, say, and I is the current index of the element where we are, and N, let's say N is the total number of images. Size is the total number of. Okay. So if I, which is the current element, if it is equal to size, I is the current element and the index. If the current index is equal to size, that means greater than equal is like equal is fine. That means that we have crossed the array boundary. So array is this is your array, and it has size. This is the size of the array, and I is starting from index 0. And if you have crossed the size of the array, then you can return, and you have not found an element, you can return -1. -1 will indicate that the array doesn't have it. Otherwise, if ARRI is equal to K, that is the ith element in the array is equal to K, then you can return I. Otherwise, if that is also not true, then you will say, okay, return recursive search, that is search recursively in this array for element K starting from index I plus 1. And size doesn't change. So here what we are changing here is only I plus 1. So here you are saying, okay, that I am at index I, and index I is neither greater than the size, that is we are still inside the array, and index ith element is not same. That means the element is on the right hand side. So look on the right hand side. That is look at index I plus 1, that whether is that element equal to K or not. So we are recursively searching for that element K in the array from index I plus 1 onwards. So this will be your first one. Is the algorithm clear? So how will and it will work almost in the same manner as video iterative algorithm. But here now you are asked in the question that what is the recurrence relation for this array of such recursive algorithm? So recurrence relation is the way to write the time complexity of the algorithm in terms of an input set. Okay? So initially when you invoke this recursive search method, let's say your array has n elements. Your input size is n elements. Then in your one iteration, in this it has n elements. Okay. Your input has n elements. Then in this recursive search algorithm, you are looking at one element. Here, you are looking at one element. At, let's say, if this was your array, and if this above 1 is your array, then you will look at this element, and you will recursively call the search on the rest of the elements. Okay, so you look at one element at a time, and then you discard that if that element is not equal to k, and then you search in the rest of the elements. So your search space has reduced by one element. You have discarded one element. Your search space has reduced by one element. So in terms of your recurrence relation, we will write, okay, T of n, that is the time complexity of this recursive search algorithm, where input size of n is equal to T of n minus 1 plus 3. Which means that, okay, in this particular iteration of recursive search, I did some constant work. What is that constant work? We compared I with size, we compared array of I with k. And that is a constant amount of work, because uh, in general, if it is not a loop iteration, or if it is not a so generally, if it is not looped, there are simple statements like if else conditions. Then if all those or some addition operation or anything, there comes in constant. So it's constantly order of one complexity. So you're saying, okay, I did some constant amount of work in this uh, particular call of recursive search function, and now I have decided that I need to look in the rest of the n minus 1 elements. So the time complexity is T of n is equal to T of n minus 1 plus 2. So when you will look at the rest of n minus 1 elements, you will the recurrence relation will be like that. Okay, now if you add n minus 1 element, then you are going to do some again constant work in this iteration, and you're going to add the next n minus 3. So let's look at the options also. So what is the recurrence ratio for the unit process? Here it is going to be n minus 2 plus 3. But in one call of recursive algorithm, we are able to reduce the search space only by one element, not two elements. So option A is incorrect. Second is saying twice of Tn minus 1. No, but we are not calling the recursive algorithm. We are calling the recursive algorithm only once. Okay, we are not calling it two times as here. Here we are calling the recursive search only one time. So that's why there is only a one coefficient here. It's not 2Tn minus 2. Okay? And then your third option is Tn minus 1 plus Tn minus 1 plus 3. And then B is Tn plus 1 plus 2. Well, we may be confused between C and D because if you look at the algorithm, it's I plus 1. But I plus 1 is you are going to look at index I plus 1, but your search space has reduced from earlier if it was n elements, now we are going to look at n minus 1 element. This element is gone. So your input space, this whatever is inside this T of this is your input size. Okay? So this has reduced by 1. So it becomes Tn minus 1. So that's why option C is there. Any questions? Okay. So moving on to the next one. It says given an array, this is your array with elements, and your key is 45. What are the mid values generated in the first and second iterations of? I think the question is asking for binary search. So if you do a binary search on this array and the key you are looking for is 45, then what are the mid values generated in the first and second iteration? So that's the question. get that on the whiteboard. Copy the inputs here. Okay. This is your input which are given, and the key that we are looking for is 45. Which is very simple. So we are looking for is okay. So let's see just discuss how does binary search work. Binary search, we are going to, so first of all, binary search works only on sorted array. And if this array is sorted, so all of the elements are here in ascending order, so this array is sorted. So that we need to make sure that's true. Now we look at how do we iterate in binary search. So first of all, when we do binary search, we find the mid element. Okay. How do you find the mid element? You will look at the first index of first element, first plus last divided by 2. So here first element is at index 0, last element is at index 7. Okay, so therefore your mid here is 0 plus 7 divided by 2, and this is float. You're taking float. So 7 divided by 2 we will see the 3.5. So that is 3.5 for the floor is. So your mid element is at index. So this is your mid. And what is that? What is array of mid? Array of mid, which is array of 3, is 89. Okay. This is what is the question now? It says, okay, what are the mid elements, mid values corresponding in the first and second iteration? So in the first iteration, the mid element is 89. So that means either B or C option is correct. Now we need to run one more iteration and say what is the element and what is the middle element in the iteration. Now what are you looking for? You're looking for 45. Okay. Now you need to here ask the question that, okay, I'm looking for 45. Can I find 45 in the left hand side of the array or on the right hand side? You have divided your array into two halves from the middle point. Okay. Now 45 is not equal to 89 here. That means your search is not over. Now your question is whether I can find 45 in the left side or the right side. Now since 89 is greater than 45, so you have to look in the left hand side of the array. So that means your search space now is 20, 45, 70. This is your search space. 0, 1. Now here your first is now at 0. That is the first, your first element is at 0. And then your last element is at index 3. And your mid element is 1 plus 2 divided by 3. It is 3 divided by 3. Okay. The array of mid is 45. This is your middle element. And what are you looking for? You're looking for K, which is also 40. So you have found the element. But the question is asking what are the middle values in the first and second iteration. So these are 89 and 45. That is your experiment. 89 and 40. Option number 1. Any questions? Right. Yeah. Okay, fine. Let's look at the next one. So it says consider an array of elements A. This is your array with 7 elements. What will be the resultant array after third pass of insertion sort? Are you familiar with insertion sort? Okay. Okay, here we have an example of our insertion sort. We're looking at this website Geeks for Geek. Here the example is that if your array has these 5 elements, 12, 11, 13, 5 and 6. So what is sorting? Sorting means you need to arrange the elements in an ascending or descending order, in some order. So the result, so the output that you're looking for is that these elements will be sorted in, let's say, an ascending order. That is, the final array should be in some order, say 5, 6, 11, 12 and 13. That's your final goal here. But originally this array is in this random order 12, 11, 13, 5, 6. So what are you going to do? In the first pass, it is saying initially the first two elements of the array are compared in insertion sort. Okay, you will take the first two elements 12 and 11, you'll compare them. Compare means you'll ask, okay, is 12 less than 11? It says okay, no, they're not. So you will swap their positions. Okay, 12 is greater than 11, hence they are not in the ascending order, and 12 is not in its correct position here. Thus we swap 11 and 12. Now 11 will be at index 1, 12 will be at index 2. Here I am saying index, assuming that index in the array starts from 1. Okay, so now 11 is stored in a sorted subarray. Subarray means that not the entire array, but if we consider our array to be only of two elements, that is 11 and 12, then they are sorted. 11 is coming before 12 and it is sorted. Okay, now what do we do in the second pass? So in the second pass here, we move to the next two elements and compare them. So we leave 11, we go to the next two elements. Now they are 12 and 13 here, and we compare them. So is 12, we ask again, is 12 greater than 13? No, 12 is less than 13. That means 12 is in the correct position. So we do not need to swap anything here. Okay, no swapping will occur, and 12 is sorted, and now 12 is also sorted in this subarray. Okay, now in the third pass, we again go to the next two elements 13 and 5, and now two elements are present in the sorted subarray, which are 11, 12. Now moving forward to the next two elements, which are 13 and 5. So we are here checking 13 and 5. Now is 13 less than 5? That is the question, which is not true. So we will swap again. So 5 will come before 13, and that's it. Now we again check, is 5, we after swapping elements, now 12 and 5 are not sorted. So we are going to check for these two, whether 12 is less than 5 or not. Not true. So we swap again. So 5 will come here. Now we'll compare 11 and 5, and then we will swap them also. Now 5 will come here. Now the fourth pass. Now the fourth pass, we again look at position. Now 5, 11 and 12. These are sorted. Now moving to the next two elements, 13 and 6. Okay. So here basically we're going to look at 6, and we are saying, okay, is 6 less than 13? Yes. So we swap. 6 will come here. Then we will compare 6 with 12. Will come here. With 6 with 11, which is also greater. So here, and finally the array is completely sorted. So in this algorithm, basically what we are doing is that we are choosing an element, and we are trying to push that element into its correct position. Let's look at this. Maybe this will be this. Yeah, so this is like an illustration. So what it is saying, this is how insertion sort will work. So if this is your original array 4, 3, 2, 10, 12, 1, 5, 6, and this is your final array which you want 1, 2, 3, 4, 5, 6, 10, 12, that is in the sorted order. So first of all, you leave the element 4 as it is, okay? Don't, you start from the second element and you check, you try to bring this element into its correct position by comparing it with the previous elements, okay? You compare 3 with 4. Now you will say, oh, you'll find, okay, 3 is less than 4, but 3, that means 3 is not at its correct position. So you will swap. Now 3 will come here, 4 is at the second position. Now these two are sorted. So you go to the next element 2. Now 2, you again compare with 4. So 2 and 4, if you'll compare, you'll find, okay, 2 needs to be swapped with 4. 2 will come here. Then 2 is still not at its correct position because 2 is less than 3. So you will swap it again and then it will become 2, 3, 4. Then you come to 10. Now 10 you will find, okay, 10 is greater than 4. That means it's greater than all the elements which are in front of 4. So it will remain here. Again for 12, it is the same. 12 is greater than 10, so you don't need to do anything. Now for 1, you will compare it with 12. You swap, then you will compare, 1 will come here, 12 is here, okay? Then you basically you swapped 1 and 12, okay? Now 1 is at position of 12 and 12 it as at position of 1. Now you will compare 1 with 10 and you will find, okay, 1 is still not at its position, correct position. So you will again swap and you will again swap until 1 comes at the head of this array, first position in the array, that will be here. So now the array after this will become 1, 2, 3, 4, 10, 12. Then you, 5, with 5 you will have to make these 2 swaps, and with 6 you will again have to make 2 swaps. Is this clear, or I need I can again explain, or I can explain this on sure. Let's look at bubble. I have to see once. Let's look at bubble sort. But is this clear? How is this working? In bubble, we actually compare them pairwise. We don't, they don't have an example in that diagrammatic form, but okay, let's look at this. So if this is your array 6305, so 6305, you will first take the two elements here, 6 and 3, and if they are not in correct order, which is the ascending order, you are here going to swap them, so they'll become 3, 6. Okay, then you will look at the next two elements, 6 and 0, not again, they are not in order, so you'll swap, so it will become 0, 6. You look at another next element, 6 and 5, not in order, you swap 5, 6. Now this was your first pass, okay? Basically you look at two adjacent elements. If they are not in order, you swap. Then in your second pass, you will again start from the first pair, 3, 0. Is it 3, 0? 3, 0. Yeah, this is your array after first pass, okay? So you look at this. So it is 3, 0. You look at 3, 0, they are not in order, you swap. So it becomes 0, 3. Then you look at 3, 5, they are in order, so no need to do anything. Then you look at
5 and 6, again there is no need to change here. Okay, then this is your third pass. You go and look at 0 3, no need to do anything. 3 5, no need to do anything, and 5 and 6, no need to do anything. So that when you find that there is no need to, there was no swap in a iteration, then you say okay, the array is sorted. So in bubble sort, you actually basically you are looking at two adjacent elements and you just say okay, whether these two elements are this is your array. So in bubble sort, you are going to look at the two adjacent elements every time and you check whether they are in correct order or not. If they're in correct order, then fine. If they are not, then you swap. Then you look at the next two elements, the next two elements. Like you look at the pairwise adjacent elements in this manner. This is, and you do this once over the entire array and you will get some new array. Okay, and you do this once, and if there was no swap, if no swap happened in this iteration, then you can declare okay, the array is sorted. If a swap happened, then you need to do the next iteration. Okay, while in insertion sort, you had this array and you look at one element at a time. Okay, you start from the second element and you try to position it at its correct location. Okay, so like in that example you had 4 3, say 4 3 2, the other elements I'm forgetting, say 10. So here you look at 3, you swap it with 4 and it will become 3 and 4. Then you have 2. So in next time, now you know okay, these two are sorted, I don't need to touch them. You look at the next element 2 that you need to place at its correct position. So you will swap it with you will check it with the previous element, and if they are not in order, you will swap. So you will, it will become 2 4. Okay, then 2 is here. Now you again check it with 3, it is still not in correct position, so you again swap. So this was your first iteration actually, and this is your second iteration. In insertion sort, you're looking at, you're taking one element and trying to place it at its correct position by comparing it with the previous elements. You in every iteration of the insertion sort, you're if you are at index say I, then the array which is from index 0 to I minus 1, that is actually I shouldn't say here, but if this is your array and you're currently at index I, and that means your elements from index 0 to I minus 1, they are actually sorted. Okay, and the elements from I to last, they are unsorted. And you're looking at ith element and you're trying to place that ith element at its correct position, which is different from bubble sort, because in bubble sort you just look at two pairwise elements every time and you check okay, whether they are in correct order or not. If they're not, then you just swap them, and you will do that until there are no more swaps in the array. That when there are no more swaps required, that means the array is sorted. So does that explain the difference between bubble sort and insertion sort? Okay, so now, okay. Now the question is here, consider an array of elements this. What will be the resultant array A after third pass of insertion sort? Can you try this? Try to answer this question. Third pass. Okay, let's look at it on the whiteboard. Hmm. This is your given array, and you are asked to sort this using insertion sort and then find the resulting array at the third iteration. Okay, so in the first iteration, you are going to take the first two elements and you are trying to sort them. Okay, so sorting two elements is just checking which is smaller or bigger. So first iteration, 4 is smaller than 10, so it will be 4, 10, 7, 23, 67, 12, and 5. Okay, this is your resulting array after the first iteration. Now second iteration. Second iteration, you're going to look at 7. Okay, now you're trying to place 7 at its correct position. So you compare this with 10 and you ask, okay, is 7 greater than 10? It is not, so you swap. So 7 will come here, 10 will be here. Now 7 is here, so you check, okay, 7 is greater than 4. Yes, it is. So we don't need to swap it with 4. So it will remain here. So this is your resulting array after the second iteration. Now third iteration. In third iteration, you will look at element number here. Element which is at position number is 4th and 23. So you compare 23 with 10 and again you are asking, is 23 greater than 10? Yes. So you don't need to swap it with 10. If you don't need to swap it with 10, it is great. So that means it is greater than all of the elements which are before 10 also, right? So don't need to do anything here basically. And it is same as before. So this is your array after the third iteration. Now in the fourth, this is actually your answer, but let's just finish this. In the fourth iteration, you will look at 67 and you will compare it with 23. It is still greater, so you don't need to do anything. So it is same. Now fifth iteration. Fifth iteration, you are going to look at 12. Okay. Here we're looking at fifth iteration, 12. Okay. Now you will compare this with 67. Okay, now 12 and 67, if you will compare, then 12 needs to be come before 67, so you will swap. So now 12 will be here, 67 will come here. Okay, then you compare 12 with 23, which is also greater. So you then again swap. So 23 will come here, then you 12 will come here. Okay, then you compare 12 with 10, which is fine because 10 is smaller than 12, so no need to swap. So this is your array after the 5th iteration. Now in 6th iteration you are going to look at last element, which is 5. Now 5 you will compare with 67, you'll swap, then you will compare with 12, 23 swap, then you will compare with 12 swap, then you compare with 10, it needs to be swapped, and then you compare with 7, it needs to be swapped. So it will need to swap all of these times, and I'm not writing the in between arrays. So finally this will be your array at the end of the 6th iteration after all the swaps are done. And this is your sorted array. Now your answer is third, which is 4, 7, 10, 23. Okay, 4, 7, 10, 23. So that is option number B. Is there any question? Okay, if not, let's look at the problem number 6. So this is our, this I think is a easy problem. So it's just asking you that, okay, which of the code snippet performs unordered linear search iteratively? Okay, so which of the following code is doing a iterative linear search? So here there is a little bit of typo. It's int unordered. There is a space between them, and it is taking an array, a size of the array, and some data that you are looking for. Right. And there are 3 code snippets. These are A, B, and then there is C. So first look at A. Here you have defined an index integer. Then you are going over the array from I equal to 0 to I less than size. You're checking if array I equal to data, then index I equal to I. So index is equal to I, and you break and you return the index. In second option, you are going over the array from 0 to less than size, and you're checking if array I equal to data, then you break and return index. And in the third option, you are going from 0 to I less than equal to size, and if array I equal to data, then index is equal to I, and then you continue and you return index. So your question is, which of the following is the correct way of doing an iterative linear search? Right, that is correct. So A option is correct. We are going to look for elements from I and less than size. We are not looking at size because the element at array of size is, because the index is starting from 0, so the element at index size is actually out of the bounds of this array. And then we are going to check the element at index I, compare it with data, and if it is equal, then we assign I to index and we break out of the loop, and then we return index. Okay, problem number 7. Which of the following inputs will give worst case time complexity for selection sort to sort an array in ascending order? So I think we discussed insertion sort, but we did not discuss selection sort. So are you familiar with selection sort? Okay. Can you answer this? That what will be the worst case time complexity for selection sort? To sort an array in ascending order for these options 1, 2, 3, where 1 is actually in ascending order, and second is in descending order, third is in some random order. So what will be the time complexity for selection sort in all of these cases? 1, 2, 3. No, it's asking B, which is second. What's okay? What is the worst case time complexity of selection sort? So the worst case time complexity of selection sort is order n square, right? You need you do like n square comparisons in selection sort. Basically, that means to say that now in selection sort, let me just quickly go over the algorithm, and then I'll explain the answer. We will use this. Okay, so if this is your array 14, 33, 27, 10, 35, 19, 42, 44, then you first, you here basically what you do in the first iteration is you try to find the smallest element in the entire array. So you will go through all of the elements and find the smallest element, which will take how much time? It will take n time, order n time, because you're looking at every element in the array, right? You're looking at every element and you're checking, you're finding which is the minimum element. So you will look at 14. Now 14 is small. You will say, okay, 14 is the smallest so far. Then you will compare, you'll go to the next element 33. You'll check, is 33 less than 14? No. So then you go 27. Is 27 less than 14? No. You go here. Is 10 less than 14? Yes. So now the minimum is 10. Then you go 35. Is 35 less than 10? No. 19 less than 10? No. 42 less than 10? No. 44 less than 10? No. So you have found in order n time that the smallest element in this array is 10. So now what do? That you take that element which is at here in position 4 and you swap it with the element which is at position 1. So after this swap, this is your new array 10, 33, 27, 14, 35, 19, 42, 44. Now 10 is actually at its correct position. Why? Because this is the smallest element of the array and it should be at the first position and it is at the first position. So now you do not do anything with 10. Just leave it there, and in the rest of the array, starting from 33, you will look at the next smallest element. Now you will go through all of these elements and you will find, okay, 14 is the next smallest. Here we are depicting, highlighting it with this pink color, and it is saying, okay, 33 is at second position, but instead of 33, 14 should be at the second position because this is the second minimum element. So you come swap 14 and 33. Now 14 will come at second position, 33 will be here. Okay, now 10 and 14 are at their correct positions because they are the first and second minimums. Now you again go in the rest of the array starting from 27 and look for the next minimum. The next minimum here is 19, which is highlighted by pink. So you will swap 19 and 27. So here 19 will come here, 27 is gone back. Okay, now again you will repeat this, and now you will try again to find the next smallest, which is 27. You swap with 23, and now 27 is also its correct position. So now 35, you go to the next position here, and you're looking for the next smallest element to come here. So 33 is the next smallest. You swap with 35. Now 33 is here. Now the rest of the elements 35, 42, 44 are in order, so you don't do anything there. But so what is happening here in selection sort is that in every iteration of the selection sort, you are looking at the elements, finding the smallest and putting it at its right position. Okay. So first smallest minimum, first smallest element is at first position, second smallest at second position, third smallest at third position, and so on. Now your algorithm, now how will your algorithm work on an array which is already sorted? If this is already sorted 1 2 3 4 5 6 7 8, now in this example you will first, what will you do? What will the algorithm do? The algorithm will try to find the smallest element, right? It will go through all of these elements and try to find, okay, which is the smallest element. You will find, okay, if 1 is the smallest element, let's swap 1 so that 1 is at its correct position. So you will just swap 1 with the element which is at index 1, and actually there is no swap, but in a sense that is what is going to happen. Now you will look for the next smallest in the rest of the elements, and you will again find, okay, 2 is the next smallest. What I'm trying to say here is that you don't know magically that which is the next smallest element. You have to go through all the elements, irrespective of whether your array is sorted or not. You have to go through all of the elements to find the smallest. So in the rest of the array, okay. So even though your array is sorted in option number 1, the time complexity of selection sort is order n square, because in every iteration you are going to look at all the elements and find the next smallest. And that is true for second also, which is sorted in descending order, and third, which is unordered. Yeah, so then option D is correct. Option D, that is, so the worst case time complexity of selection sort is order n. So the worst case and the best case, they're same for selection sort. Like it's always order n square. It doesn't matter that what is the array, like it whether the array is sorted or not. It's always order n square. So that's why option D is correct. Now, what is the best case for bubble sort? What is the best case time complexity for bubble sort? If you are given, okay, the same question. If you have option number 1, I'm asking that if you have a sorted array, then what is the time complexity for bubble sort? Okay, so in case of bubble sort, the time complexity when the array is already sorted is n, order n. Why is that? Because you will go through the array once and you will look for, like, you will look at adjacent elements, right? uh, and if they're not in order, then you swap. But if you have the array already sorted, then there'll be no swaps. And if there are no swaps in an iteration, then that is the condition to terminate bubble sort, right? So that means you will go through the array only once, which is order n, and then the time complexity is order n. So if that is not clear, then let me know. Otherwise, let's move to the next question. Here we have an array A, and you have to apply the insertion sort to sort the array. Consider the cost associated with each sort is 25 rupees. What is the total cost of insertion sort for sorting the entire array? I think
Okay.
option D. Okay, can you explain how?
For iteration to sort.
Yeah, sorry. I did not understand. Why the insertion sort? I'm a little confused with the question, but I think each sort means one iteration, I think. Not one iteration. I think each sort. Probably it means each iteration where you require to sort. Yeah, what was your answer?
100.
100. How is it 100?
If you sort the given array
Yeah,
A step by step,
yeah.
then in how many steps we will be sorted this array?
Yeah, steps are 4. But I think the question is saying that if if in so the steps are like iterations, so there are 4 iterations that I understand, but I think it is saying if an iteration requires you to sort, then the cost is 25. In an iteration, if you did not require to sort because the array was already sorted, then I think there is no cost. So out of these 4 iterations, how many iterations require you to do some sorting? Okay, so let's look at it on the whiteboard. Oh, 54913. 54913. This is your array, and we have to sort it using insertion sort. Okay, so first iteration, what are we going to do? First iteration, we are going to look at 4 and 5, and we are trying to place 4 at its correct position. Okay, so we'll compare 4 with 5, and 4 is less than 5, so there is a swap. Okay, and this is your output array after the first iteration. So since there is a swap in this iteration, this will cost you 25 rupees. Okay, now second iteration. Second iteration, we are going to look at next element. 4 and 5 are correctly sorted. I mean, we look at 9. Okay, now we compare 9 with 5. Is 9 less than 5? No. So there is no need to swap. So this cost you 0 because there was no swapping required here. Third is you will come at this position where 1 is, and you check 1 with 9. Is 1 less than 9? Yes, so you swap. So 1 will come at position 9 will come basically here. Okay, at position of 1, then 1 is here. Now you compare it with 5. Is 1 less than 5? Yes, so 5 is also swapped backwards. Now 1 is compared with 4. 4 is 1 less than 4? Yes, so 4 is also swapped backward, and 1 comes at position 1. So this iteration also costs you 25 rupees, I think. Then fourth iteration. In fourth iteration, you will look at the last element 3, and you try to position 3 at its correct place. Okay, so you will compare it with 9, and you will swap. So 9 will come here. Then you will compare 3 with 5. 5 will be swapped backwards. Then you will compare 3 with 4. It will also be swapped. Then 3 will come here. You will compare it with 1, but that will 1 is smaller than 3, so no need to do anything. This is your output. This will also cost you 25. So total it's 75, which is, so the correct option is C. So here the wording of the problem is a bit tricky because I think it's not very clear what the question is saying. It's saying that consider the cost associated with each sort is 25. So I think it means that in each iteration, if a sort happened, if a sort was required, then the iteration will cost you 25 rupees. Then what is the total cost of insertion sort for sorting the entire array? So if I interpret it like this, then the answer is 75. But if there is any other interpretation, like one other way, I thought that maybe it says that each swap is 25, then there are too many swaps and there is no other option for that. Does that make sense?
Yes, ma'am.
Yeah, questions to answer Nishu's question, that are the questions in live session 1 and 2 are same or not? I think they're same. We all cover the same set of problems. But Rohit said it is not same.
Some questions are same, but some are not.
Okay. I think most of them will be same.
Yes, sir, both is the same.
Okay. Okay, let's look at problem number 9. A sorting technique is called stable F. Therefore, option it takes n log n time, it maintains a relative order of occurrence of non-distinct elements, it uses divide and conquer, and it takes order in space. Any answer? Okay, so
No, ma'am.
okay. So option B is correct. It maintains the relative order of occurrence of non-distinct elements. What are non-distinct elements? Like your array can have repeated elements, like 2 can come say 2 times or something like that. So just taking an example here. If this is your array here, 2, 5, 2, 3, 6, 9, let's say. Now there are two element, the element 2 is repeating here. Okay, let's call this 2a and this called 2b. I'm just using a and b here so that I can distinguish between these copies of 2, right? They're non-distinct. Value 2, they both have value 2, but I'm just using a and b as a subscript. They're still value 2. Now one sorted array can be 2a, 2b, 3, 5, 6, 9. And there can be 2b, 2a, 3, 5, 6, 9. Like both are sorted. Okay. Both are sorted right here. 2, 2, 3, 5, 6, 9. That's the order. But the first one is stable. The first one is called stable. Second one is not stable. Stable means that the position of the elements which are not distinct, that will remain same. That is not going to change. So 2a came before 2b, so it is coming in the same order even in the sorted array. While in this sorted array, their positions have changed. So this one is not stable sorting. And above one is stable sorting. And some example of sorting algorithms which are stable by nature are merge sort and insertion sort and bubble sort, while selection sort is not stable. Okay, stable sorting algorithms are merge, insertion, bubble, and non-stable are quicksort, selection sort. Is it clear that what is a stable sorting? So if there are elements,
Yes,
okay, if there are elements in your array which have the same value, then the order in which they are coming in the sorted array, if that is not changed, then that is stable. If that is changed, then it is not stable. Here I'm using subscript a and b only to distinguish between these two copies of 2. It is not there in your input array actually. So it maintains the relative order of occurrence of the non-distinct elements. Now coming to question number 10. The average case occurs in the linear search algorithm when? So average case, and there are three different kinds of analysis of algorithms. One is best case, then there is worst case, and then there is average case. So it's saying that
Option A will be correct.
yeah, so option A is correct. The average case basically makes some assumption about the relative frequency of inputs. Okay, and so when the item to be searched is somewhere middle of the array, then the average case occurs in a linear search algorithm, which is that the time complexity is order of n. Okay, let's look at the programming problems. Okay, the first problem is that you have to write a C program to reverse an array by swapping the elements and without using any new array. So if this is your test case, first these are the elements. There are 7 elements here. Okay, first this is 7 is like how many elements are there, and then these are the elements 8, 9, 10, 6, 4, 7, 11. Then you have to reverse it. Reverse means it will be 11 will be at first position, and then 7, 4, 8, 6, 10, 19. Now question is saying you have to reverse the array, and you cannot create a new array. You have to reverse the given array, and it is giving you a way also, that is you can swap the elements. Then how will you do that?
I think we already did this programming assignment in our earlier class.
Yeah, I think we did a similar problem. But can you still go with it?
Yeah, actually, here the number of elements are already given, so we can simply apply for loop to the given number divided by 2 and swap the elements.
Swap which elements?
First to last.
First to last. Then what do we do in next iteration?
What in next iteration?
Huh? What do you do when you have swapped first and last element?
Yeah, if you can using by simply taking a temp variable.
No, I'm not asking how do you swap. Let's say you swapped, then what do you do next? You took the first element, you took the last element, you swapped them. Fine. Now, then what do you do?
Then our for loop will be executed and our array will be swapped reverse.
But how? I mean, what happens next? In that iteration of the array, what will change?
Like if we use for loop,
Yeah.
yeah, and we will swap the given array.
Yeah.
Yeah, and in next we will decrease the, like if we arr I is equal to arr n.
I
Then in next iteration I is equal to I plus plus and n will be n minus minus.
Okay. Okay. Yeah, so we have here 2 pointers, okay? This is our pointer 1, P, let's say called P. This is Q. P is initially at position at the first element in the array. Q is at the last element in the array. Okay, we will swap the elements which are at position P and Q. Okay, that's what we are going to do. So in the first iteration, we have P is at here at first element, Q is at the last element. We are going to swap them. So now our array will become resulting array after the, like, we will swap these two basically, and it will become 13, 6, 7, 8, 10, 11, 12. Okay, this is our array after that, and our P and Q, P will be incremented, Q will be decremented. Okay, so they are moving like this towards each other from the two ends of the array. Okay, from the left, P is at left end, Q is at right end. Then we swap these two elements and we move P and Q towards each other like this. Then we will again swap. Okay, again swap them. So now this will become 12 and this will become 7. And they will, pointers will be moved. Q will come here, P will go to 8. Again we will swap 8 and 11. So now here 11 will come, here 8 will come, and then we will increment P, decrement Q. Now P and Q are at the same element. So then we will stop. Either they become, like, basically when P is no longer less than Q, we will stop. So it's no longer less than Q, so we stop. So in this way we have swapped, we have reversed the array with swapping. Okay, let's look at the code here. So first we scan the number of elements and then we scan all the elements in the array. Okay, here then here we have end, which is, I said, Q. So Q is, or the end of the array, which is n minus 1, initialized to n minus 1, and the start of the array is C here. C is initialized to 0, and we are going from 0 to n by 2, that is the mid of the array. Okay, and we are going to swap the element at C with the element at position end, and we are decrementing end at every iteration and incrementing C at every iteration. Okay, so it is same at what I just described. You can write it in a for loop like this, and you can also write it like a while loop. Okay, then you just print the reversed array. Is there any question?
No.
Okay, let's look at the next one. This is, write a program to search a given element from a 1D array and display the position at which it is found using linear search function, and assuming that the index location starts from 1. Okay, so for example, this is your test case. It says, okay, 4 elements are there in the array. So first input value is the number of elements in the array, which is 4. Then the 4 elements are 45, 65, 85, 25. And the last, it is saying, okay, you have to give me the position at which 95 is present in the array. So this is your array 45, 65, 85, 25, and it doesn't have 95. So the output is 95 is not present in the array. So you have to write a program to do this by doing linear search. How will you do?
Simply we create a function of linear search.
Okay.
In which we take input from main function, the array element, and the size of the array.
Yeah.
And we initialize index as an int.
Okay.
Yes, and we will search the element
Yeah. What do you mean by search?
Yeah, by using linear search, by using for loop.
Yes.
If element is found, then we will initialize the index is equal to I and we will break the loop
Right. Yeah.
and we will return the value of I, that is index. And if the for loop is closed, then we can return index is equal to -1.
Right.
In that case, the element is not found.
Right. That is right.
Yeah.
Okay. So just let's quickly go over the code. So here we have, we first scan the number of elements, then we scan the elements in the array, and then we scan the element which we are searching for. Okay. Then we have created a linear search function here, which takes as parameters the array A, the number of elements in the array, and the element that we are looking for. And here what this is doing is that there is a for loop which is going over all the elements in the array from 0 to less than n, and it is saying, okay, if a of c is equal to find, then return c, that is return this index. Otherwise, if you come out of this for loop, then return -1. Okay, that works because we can just simply return here. Okay, it's same as what you said, or we can break also. And then it is we are calling this function linear search from the main, and in this linear search we are passing array n and the search element, and it will return us the position. If the position is -1, then we print that the element is not present in the array, and if it is not -1, then we say that the element is present at location position. Here we have done a correction, which is like here we are using index from 0 to less than n. So the question asks us to report the answer assuming that the index starts from 1. So that's why we are doing here +1, position +1. I mean, that is something that you need to be careful with. Okay. So the last question is, write a C program to search a given number from a sorted 1D array and display the position at which it is found using binary search. So the same question, but with binary search. You have to search for an element in the array using binary search algorithm. Similarly to before, first input value is the number of elements, which is 6. So the 6 values are your input, and then 2 is the search element, and here 2 is at position 2 here, so 2 found at location 2. That's your output. Now you have to here implement a binary search. So how do you implement a binary search? Do you want to think about it, or I should go over the code?
Yeah, we can search by binary search.
Binary search. Yeah, that's what the question is saying.
But I can't find the index.
You can't find index,
Yes.
but that's just a bookkeeping. If if your element matches, then you, similar to previous time, you just keep a variable index and update it.
Hmm.
Or similar to before, you just return whenever your element you're looking for is equal to the middle element, you can just say, okay, return this index.
Yeah, then when it is equal to middle element,
Yeah. Okay, let's look at the solution. So again, similar to before, we will read the number of elements, we will read the array, and then we'll read the element to search for. So here in binary search, as we discussed previously in the class, that we first initialize two variables like first and last. So first element here is at position 0, last element is at position in -1, that is the entire array, that is your search space right now, and middle element is at first plus last divided by 2. Okay, that is your middle element. Now you are going to go over you're going to then take this while loop, and this while loop you will run until first is less than equal to last. Okay, and in every iteration of the while loop you're going to check first that if the array element at the middle of the array is equal to the search element, then you can just print that element, print that the element is found, and you can break out of the loop. But if it is not equal to the middle element, then you check whether the element, you compare this search element with the middle element. Okay, if the middle element is less than the search element, that means that all the elements in the left hand side of the middle are also less than search. So search element cannot be found in the left hand side of the array. So you need to go to the right hand side. So you update your first pointer. That is, now your array starts from middle plus 1. Okay. Otherwise, if your array of middle element is greater than search, that means all the elements including middle in the right hand side are greater than search, so you won't find search there, so you look in the left hand side. So when you want to look into the left hand side, you update the last of the array as middle -1. When you want to look in the right hand side, you update the first as middle +1, and when you want to look in the left hand side, you update the when you want to look in the left hand side, you update the last as middle -1. And once you have updated first and last, you will again compute what is middle now, and then that will be used in the next iteration of the while loop. So I'll go over it once again. So what I'm saying here is that you will first initialize, since initially your search space is the entire array. Okay, so in binary search we have these three variables which are very important. First is here they're calling it first. Okay, that is marking the start of the array. Last is means the last what is the last index where of the array. Middle is the middle index of the array. Okay, you have first, you have last, you have middle, and middle you compute by adding first and last and dividing it by 2. So first is 0, last is n -1, middle is first plus last divided by 2. Now you have this while loop which will run until this condition becomes false. But the condition is that first is less than equal to last. So until first is less than equal to last, this condition will be true. Okay. Now I just want to make a small change to the code here. Okay. So first, when we enter this while loop, we are going to check if the array, if the element at middle index, if that is equal to search, that means we have found the element, and we will just print what is the location of where it is found, and we will break out of the loop. Okay. Otherwise, what we do is we have to decide whether to search in the left side of the array or in the right hand side of the array. How do we decide that? We decide that by comparing the element search with the middle element. So if the middle element is less than search, if it is less than search, that means search is so that if the middle element is less than search, that means all the element in the left hand side of the array are also less than search, right? So we cannot find search in the left side of the array. We have to look only in the right hand side of the array. Because element at middle is less than search, all the element in the left side of the array are also less than middle element. So we cannot find search in the middle. We cannot find the search element in the left side of the array. So we look in the right hand side. How do we look in the right hand side? Basically, we update the start index, that is the first index of the array, as middle plus 1. Now our search space is starting from middle plus 1 to last. Otherwise, if the searched if array of middle is greater than search, okay, that means the middle element is greater than search. That means all the element in the right hand side are also greater than search. So search, we have to look for the search element in the left hand side. To look in the left hand side means we update the last index. The last index will be middle minus 1. And once we have updated first and last, that means our search space has reduced. Our search space has changed. Now it is no longer the previous first and last. It's a new first and last. Okay. So then we update the middle. We compute the middle element. So now middle element is, again we use the same formula, which is first plus last divided by 2. Okay. And then we will go and check the while loop condition. If it is true, then our search will continue. Whenever this becomes false, we will come out of the loop. And when do we come out of the loop? When first is not less than equal to last, that it is greater than last, and then we print not found. Okay.
Yes, ma'am.
Okay. Is there any question? Okay, I'll stop the recording. Thank you, everyone.